everybody. Start the lesson 10-2, the last part of it, I promise. We're going to look at some position, velocity, and acceleration problems, but wanted to first of all get you to think about what did you take the derivative of to get y prime equals 2x. Go ahead and write down what we took the derivative of. What was y if when we took the derivative we got 2x? All right, hopefully you got x squared there. And I want to point out something for those of you who are a little more creative or insightful. Maybe you got something like this. Go ahead and take the derivative of y equals x squared plus 3, and what do we get? Or for that matter, y equals x squared minus 7. Or y equals x squared plus 11.03. Right? Every time we take the derivative of those, because the constant rule, the derivative of a constant is 0, we get the same derivative. So that's kind of interesting that one derivative value could have come from an infinite number of possibilities, but they are all the family of a parabola that's shifted up or down, right? Straight up or down on the y-axis. So it's a family of graphs. And the way we usually say that, when we find an antiderivative, that's the opposite of the derivative, we would just say x squared, oh yeah, could have been plus a constant. And that's a capital C that I'm using, is pretty typical. Okay, so keep that in mind that there are a family of graphs here when you're trying to find what you took the derivative of. Don't forget there could be any constant there. Alrighty, let's go ahead then. That's kind of one of the basics for the next part of the problem that we're doing. And it is initial value problems. And our job is going to be to find the velocity and position functions of a body falling freely from a height of 0 meters under each of the following sets of conditions. So picture an object on a cliff, falling off down into the bottom there. And when I say body, I like just picture a rock, not an actual body. Let's not be gruesome, right? Okay, so let's look at what we've got here. So we know the acceleration. And because gravity pulls you down, we'll sign it as negative. Now we know the whole key to these problems is that relationship between position and then the derivative of position is velocity and the derivative of velocity is acceleration. So if we want to go from acceleration back up, that's an antiderivative. So you take a minute, you pause me, and you think about what could this possibly be? And I'm getting negative 1.8 t because the derivative of this takes us back to acceleration. And I hope you didn't forget that plus c, because we just kind of mentioned that anytime you're finding an antiderivative, you have to acknowledge there could be a constant there. Alrighty, and then we need to plug in something. You can't move on to find position until you figure out what that constant is. So what we're trying to find is from all the gobbledygook given information that we've got, do we have a time velocity point that we could plug in? And we totally do. It says that the body falls from rest. That means the velocity at the start, the thing's at rest, and we know that means the velocity is 0. So I'm going to plug this in and solve for our constant. The velocity should be 0 at time 0. And I think that makes it pretty easy to find that our constant is 0. And you don't have to show exactly all of that work. But I'm going to go back now and acknowledge that my constant truly was 0. And now we're going to do the same thing again. We've got to get from velocity back up to the old position. So go ahead and find the antiderivative of this. You can pause me if you need a second to do that. And I'm going to acknowledge that there could be a constant there. And I can check it by taking the derivative. If I take the derivative position, it takes me right back to that velocity, makes me very happy. And now what we're looking for to solve for this constant is some sort of time position point that we have, a time and a height, I guess. And it says that at the start, initially, time 0, the height is 0. So once again, the height's going to be 0 at time 0. This isn't a whole lot of a challenge to figure out our constant. And so we can truly be done finding that position pretty quickly. That's our position function. It will tell us that we can find for any time the height of the object. Okay, now I'm going to stop right there for just a second and change these out so we can look at some slightly different scenario. Okay, so here we go again, only there's been some little bit of changes. Something that hasn't changed is that the derivative position is still velocity, the derivative velocity is still acceleration, and we're going to start with a given acceleration, and we're going to be asked to find the velocity equation. So it means we're going to have to move back up, finding the antiderivatives. So go ahead and write down that antiderivative. Don't forget the plus c. And remember, the only way we can solve for that c is to find some kind of time velocity point in the given information. And folks, it's always going to be there. You just got to look for it. And it says it looks like the body is propelled downward with an initial velocity, that's time 0, of 1. I put in -1 because velocity implies direction, and this is propelled downward. And what I'm going to do is plug in the v, -1 for my v, at time 0. And then we can go ahead and solve for the value of c. Once you find c, now you can write your perfected velocity equation. Okay, I just plugged that c I found from our initial condition right in there. All right, now I think you know the drill. Let's go ahead and see if we can get back up here to a position function. Go ahead and find that antiderivative. Okay, now I hope you didn't forget that the antiderivative of -1 would be, negative t, right? You can always check by taking the derivative real quick and getting back to it. All right, now what do we need to find this value of c? We need some sort of time, position, information given. And I'm going to look at the initial problem here, and it did tell us that it was falling from a height of 0 initially. So this one, our initial height is still going to be 0 there. So I didn't make any changes. And if we plug in a 0 for position and a 0 for time, we should be able to pretty easily solve for our constant. And then we can make our perfected position function, which is what we were asked to find. Okay, so a couple things. You have to have a constant when you find the antiderivative. You have to acknowledge it could exist, and there has to be some initial information given for you to solve for the constant, or you can't move on. And that information will always be there. Just have to look for it. Okay, folks, that's all for me.